Well, last time we started talking about factorization type domains. And the first thing we talked about is Euclidean domains. Euclidean domains are things that mimic the integers in the sense that you've got a division algorithm. You can take two elements, y and x, both not zero, we'll say, and we can divide y by x, get a quotient of q and a remainder of r, and that remainder is either zero, which means it divided evenly, or the size of the remainder is smaller than the size of what you divided by. So examples of all these, the ordinary integers, the Gaussian integers, polynomials over a field. We talked about how basically this allows us to do partial fractions. Power series over a field. To be Euclidean, you have to have a polynomials over a field or power series over a field over any other kind of ring won't work. So let me give you another definition. This sort of suits PID definition. We say that, again, R is a commutative ring with one. We say, in fact, usually a domain, but here, Noetherian is every ideal of R is finite generated. This was actually defined in an earlier homework. So we say that a ring is Noetherian, that's named after one of my biggest mathematical hero, Emmy Noether. She was a fantastic mathematician, 20th century. And in honor of her, if every ideal of R is finite generated, we say the ring is Noetherian. So let's up the voltage. If R is a domain and every ideal principle, and that is generated by one element, we say R is a principal ideal. There's also the notion of a principal ideal ring, PIR, and that's just if you remove the assumption of integral domain, maybe it's got 0 divisors in it. So Noetherian means every ideal is finitely generated. Principal ideal domain means it's an integral domain where every ideal is in fact principal. For example, C is a PID. And actually, so are all of these. We are going to have a theorem later that if you have this condition, you're automatically principal ideal domain. And finally, here is another classic definition. Here, definition 11.2. We say R is a UFD, that's for unique factorization domain. If R is atomic and can anybody remind me what it means to be atomic?
Atom irreducible.
Like an atom is a synonym for an irreducible. It can't be broken down any further. Atomic means everything that can be factored into atoms will be factored into atoms. So that is, if it's not zero and it's not a unit, it factors into atoms. So step one in a UFD, everything that can be factored into atoms is factored into atoms. And if pi one, pi n is tornado one up to tornado m are irreducible factorizations, by irreducible factorizations is each of these pies and each of these little tornadoes are irreducible. What do you suppose it means to be unique? It means that these irreducible factorizations have to basically be composed of the same factors, right? So step one, if it's going to be unique, that better be true. The number of factors, the number of irreducible factors on the left side should coincide with the number of irreducible right on the right side, but that ain't good enough. They should pair off. So I'm going to write something fancy, but let me take it apart. There exists a sigma and Sn such that I is ui tornado sigma I for all one n and like unit r. Okay, that's a mouthful, right? What does this mean? This means pi sigma Sn is just a permutation, right? So whatever this is just another index. So what this is saying is pi I is one of these guys times perhaps a unit, right? That's all that this means. And that's where you get the uniqueness. Why do we have this crazy condition in here? Because, for example, if I factor the number 12, if I factor the number 12 into irreducible factorizations, it's not 6 times 2, right? Because 6 isn't irreducible. It's not 4 times 3 because I haven't broken those all the way down. Here's how I might factor 12 into irreducibles. These factorizations are the same, right? Because what those conditions in number 2 says is there's a permutation. What should the permutation be? Well, the permutation should take this one to this one, this one to this one, and this one to this one. And we'll see 3 is 1 times 3. 2 is negative 1 times 2. There's your unit, right? So it varies by a unit. And this minus 2 is negative, is 1 times minus 2, right? So that's all that's saying is the irreducible factorizations are the same. They just might be shuffled and there might be units. That's it. Okay, everybody get the gist of that? Okay. Now I'm going to give you some powerful structural theorems that will allow us to make some important connections later on. Proposition. So here's kind of our first big proof. We're going to prove this one. R is a PID, respectively, Noetherian. Only if every prime R is precedent, respectively, 5. Okay, so let me read this theorem to you. What this says is R is a principal ideal domain if and only if every prime ideal is principal. Or respectively, R is Noetherian if and only if every prime ideal is finitely generated. Can somebody explain why this theorem is powerful? Actually, I'm only going to prove the statement about PIDs. I will leave the Noetherian as kind of an exercise for you. It's the theory proving Noetherianness if and only if every prime ideal is Noetherian is very similar to this. There's just a little bit more to it, and it's a good exercise. Doing the PID part will get you pretty much what you need to know. Now, before I get into the proof, I want to explain why this is significant. Why is this significant? Well, here's why it's significant. This direction is trivial, essentially. If R is a PID, then all ideals are principal. That's easy, right? Because PID means every ideal is principal. So certainly the prime ideals are principal, right? What a shocker, right? The interesting part of this theorem is if all the prime ideals are principal, and primes are rare compared to this general idea, all you need is for the prime ideals to be principal and everything has to be. That's perhaps surprising. That means to check if something's a PID, all you got to do is check the prime ideals and then everything else is good to go, right? This really shows you the power because there are many rings you can build that only have finitely many primes, but they have infinitely many ideals, right? So this is the fun direction. This is where there's really something going on. So let's assume, suppose that R has an ideal that is not principal. We show there exists a prime ideal. This is the structure of the proof of an attempt, right? So we want to show that every ideal is principal implies every prime ideal is, I'm sorry. We want to show that every prime ideal is principal means every ideal is principal, right? We're showing here, we're going to do the contrapositive. So if there exists an ideal that is not principal, there has to exist a prime ideal that is not principal, right? And then we'll be done with it, right? Everybody with me on the structure of the proof? Just the existence of an ideal that is not principal gives us the existence of a prime ideal. So let I be our non-principal ideal. We are going to show first there exists an ideal that is maximal with respect to being non-principal. So this is what my strategy is going to be. I start with my seed, and my seed is that I've got an ideal that's not principal. I'm going to grow this to an ideal that is maximal without respect, with respect to not being principal. Got to show that that animal exists. And then step two is, once I have that in hand, this ideal is maximal with respect to being not principal, I want to show that that forces that ideal to be prime. And then I'll have a prime ideal that's not principal. Okay. Anybody guess what might come up? How are we going to show that there does exist an ideal that is maximal with respect to not being principal? Think about how you do this and make good choices. I bet you have to use the active choice in the guise of Soren's limit. So here's what we're going to do. Let gamma be the set of ideals J in R, such that and J is not principal. Okay, first thing I'm going to do is I'm going to collect all the non-principal ideals of R that contain I, right? Let me point out that gamma is not the empty set, as I itself is in gamma. Assuming that I is not principal, and of course I contains I, so there is one example of a non-principal ideal that contains I, right? Gamma is partially ordered under inclusion. Right? We might have a lot of apples and oranges here, but it's partially ordered by inclusion, right? That is anything that contains, if you have J sub alpha, J sub beta, then they might not be comparable, but if they do, it satisfies this partial ordering. We need to find, so to apply Zorn, we need to show any chain in gamma has an upper bound. Yeah. Okay, so let's see. Let's call this J alpha. Some index set be a chain. Can somebody remind me what a chain is?
Everything.
That is correct. It is a totally ordered subset of gamma. So instead of apples and oranges, I've only got apples, right? So as a reminder, if J alpha and J beta are in this chain, then one of them contains the other. That's what it means to be a chain, and that's gonna help us get an upper bound. Okay. So to apply Zorn's lemma, we need an upper bound of this chain. And I'm gonna go right for the throat here. Let U equal to U. Now, this is an ideal We need it to be an ideal. Okay? And it is an ideal, and it's precisely because this is a chain. Let me remind you, if X, Y, and U, and R is in R, then X is in J alpha, Y is in J beta, right? Because U is the union of these. So if X is in this union, it has to be in one of these J alphas, and Y by the same token has to be in one of these J's as well. Without loss of generality, J alpha is contained in J beta. So X and Y are both in J beta. Hence, X plus RY is in J beta, which is in. So U is not. It was extremely important in this setup that this is a chain, this is a union of ideals. That's how, because usually if I just take a union of two random ideals, I don't expect sums to be in there, but it's because this is kind of a nested union. This works. Everybody okay so far? Number two, I is contained in U because I is contained in every one of these J alphas just by definition. Okay. So what do we have? It's a subset of R. It's an ideal. Got to show the J that U is not principal. Okay. How are we going to do that? Well, you know what? Again, I'm going to go for the throat here, and I'm going to try to get a confirmation. Let's assume the U is principal. Well, I can be so it's generated by some elevated stuff, right? Now, what do we know about U? Let's go back to it. It's a union. Right. So this C is in J alpha for some alpha. Okay. Let's see the problem. Okay, they're right. Therefore, the ideal generated by Z is contained in J alpha. So U is contained in J alpha. But also, J alpha is contained in U because U is the union of all these things. So J alpha U is principal, which is a contradiction because every one of these things in here is not principal. So that's a no-no. Hence, U is not principal. So let me kind of make a little illusion here. Yes. Ideal and U is not principal. And J alpha is contained in U for all alpha. So U is an upper bound for the chain and sorts of all class. So we have an ideal, which I will call J, that is maximal with respect to being now, be careful again with the terminology. It is not necessarily a maximal ideal. It is just maximal with respect to that property. So what this means is this is maximal with respect to being not principal. It means any ideal that contains J properly. If you've got an ideal that contains it just a little bit, it has to be a principal ideal. All right? That's all this means. Our next claim, and this will kind of finish it off for us. Claim J is prime. And this will do it for us because what do we know? We know that J is not principal, and now we'll have a prime ideal that's not principal, and that will conclude our theorem. The principal part theorem. Okay, so how do we go about that? Well, let's do this. Suppose not. Let's suppose that J is not prime. What does that mean? That means there exists A, B, and R with A, B not in B, but A times B. I don't mean P, I mean J. It's right there. If it's not prime, J is not prime, I can find two elements called A and B, neither of which are in J, but their product is in J. Right? Now, where are we going to go from here? Let us consider let's consider the ideal A, capital A. This is the smallest ideal of R that contains all of that contains all of J and A. All right. Notice that this strictly contains J. Right? Because A lives in this guy, but by assumption it doesn't live in J. Right? So what can you say about capital A? If it's an ideal and it strictly contains A, then what can we say about it? What is J? It's maximal with respect to being non-principal. This ideal is a little bit bigger than J contains it. So this guy must be principal. A maximality, A, principal. So I'm going to say that A is generated by some element Y. Now I'm going to define this new ideal B. B is going to be everything in R that throws Y into J. What can I say about B? Well, notice that everything in J has this property, right? Because if Z is in J, then certainly J is an ideal. It'll throw Y into J, right? So this contains J. If I agree with that, and surely everything in J throws Y into J. And in fact, this is strict. Anybody see why it's strict? Help me out. Notice that Y is in A, which is equal to J A, right? So Y is equal to J plus some R A. J is in J, R is in R, right? Just by definition, because the element Y lives in here, so I can express it as something in J plus a multiple of A. I agree. So notice B times Y, BK plus RAB. Everybody agree with that? BJ is in J because little j is. And this is in J because we're assuming that AB is in J. So B is in capital B. Right. So B is in capital B. Hence, B contains JB, which strictly contains J. So therefore, B strictly contains J. Everybody agree with that? So what does that mean about B? So what do we know about B now? It strictly contains J, so it must be, it has to be principal as well. B is also principal, right? So I'm going to finish this up now. Now claim J is equal to AB. And notice A and B are both principal. This was generated by Y and this is generated by X. If I can prove this claim, I'm done because that's a contradiction. Because that would mean that J is principal, but we already know that it's maximal with respect to being not principal. Right? So how do I do this? Well, let me first point out that why is this the case? Well, because if you have something that lives in AB, it's Y times something in B. Everybody agree with that? But Y times something in B is automatically in J. That's by definition. So if you take any multiple of Y times something in B, then it's going to be in J just by the definition. So this is actually well. The other bit is a little bit tricky. Let's let J be in. Now, this is any J in J is certainly an A. So what does this mean? This means not to be as a multiple. Because it's an element of A, J must be a multiple of I. Now note that as J is contained in B, little j is an element of B. So, yes, R times Y equals J and B. Whoops, I'm sorry, J and J. Notice R times Y is J and J. This implies that R is in B. Right? Because by definition, R is knocking Y into J, so R is in B. Hence, RY is in BA, which is AB, rings commutative, which is therefore J is in AB. So J is contained in AB. So J equals AB. It's principal. Which is a contradiction. Well, the question is J must be. Because when we assume it's not prime, we got a contradiction. Since J is prime, we have a prime element. It's not principal. And questions on it? Yes.
Over here in this corner,
Mhm.
why does saying so B is in B imply the hence statement?
Right here.
Yeah,
So B contains JB because what we've shown is B is of course in B and everything in J is in B by construction. And since B is not in J, this is a strict containment here, which means that B strictly contains J. Is that sort of what you're asking about?
Yeah.
Okay. So y'all remember the definition of a UFD? It's atomic, and if you have two different factorizations into irreducibles and the links have to be the same and you can essentially pair them off. I've got a better one for you. Lemma. Of 6. R is a UFD. No. Every nonzero, nonunit of R is a product of primes. This is equivalent to the definition that we had before. It's much more simple. I don't have to say anything about atomic because that's absorbed in, right? Because I didn't say that everything's a product of irreducibles. I said it's a product of primes, right? And here's the beauty. Notice I didn't say anything about counting the factors or pairing them off, because one thing that's a big takeaway from this is irreducible factorizations can be different. In fact, we gave a number of examples of these. However, prime factorizations are interesting. That's kind of cool. That's a groovy takeaway. Let's see why this is true. Proof. Let's assume that we've got a UFD. It suffices here to show every irreducible is prime. This is actually the easy direction. It suffices in this direction. If you have a UFD, it suffices to show that every irreducible is in fact prime. Because in a UFD, we already know it's atomic. That means that every non-zero non-unit is a product of irreducibles. So if I satisfy this statement, if every irreducible is prime, then every non-zero non-unit is a product of primes. Everybody okay with that? So how do we show this, right? So let pi in R be irreducible. And suppose pi divides AB. You need to show that this irreducible, it must divide one of these, right? This means AB equals pi times R for some R in R. Now, right, A equals, let's say, gamma 1, gamma 2, gamma k, and B equals A to 1, A to 2, A to M. And what I mean by these are irreducible factorizations. A and so let me write this out then more grammatically. Let me point out that either A or B could have an empty irreducible factorization if it's a unit, but they can't both be units because pi is an irreducible and it can't provide a unit. So let's write this gamma 1, gamma 2, gamma k, A to 1, A to 2, A to M equals pi R. By the way, I could also factor R into irreducible factors as well, but I'm not going to bother. Right? By the way, if I did factor R into irreducible factorization, how many irreducible factors must R have? I can tell you that right off the bat. So if I were to factor R into its irreducible factors, how many irreducible factors will it have?
K plus M.
K plus M minus 1, right? Because you have to have matching on both sides. But it doesn't matter because the factorization is unique. So notice that pi is a unit multiple of some gamma I. Okay. Unique factorization, since pi appears on this side, it has to appear on this side, right? Which means that pi has got to be one of these guys or one of these guys up to a unit, right? So pi divides A or pi divides. If it's one of these guys, then pi divides A, and if it's one of these guys, then pi divides. Everybody okay with that? Well, that's one direction. How about the other? Well, suppose that every non-zero non-unit is a product of primes. So get this one. Prime factorizations. P1, P2, Pn equals Q1, Q2, Qm. I'm going to be a little bit sloppy here. But suppose that we have two prime factorizations that are equal. P1 divides Q1, Q2 up to Qm. Well, P1 is a prime, so it has to divide one of these, right? That's the big thing about primes. So without loss of generality, say P1 divides Q1. This implies that you can divide out up to a unit. So P2 up to Pn equals U, Q2 up to Qm. And now go by induction, right? So basically what you've shown is P1 and Q1 pair off because they're the same prime. Now P2 divides this, it doesn't divide the unit. Just keep going like this, and you get that N equals M, and your uniqueness is a step along as we go. Okay, any questions on this? Okay, so I am going to give you two theorems that I'm not going to prove until next time. But this is kind of a look ahead at how everything ties together at the end game. Proposition 1127. Here, we need R to be an integral domain. Following are equivalents. One, R is a unique factorization domain. That is, everything can be written as private primes. It's not zero, not zero. Every prime ideal of R, every non-zero prime ideal of R contains a non-zero prime. This is once again, it's a Zorn's lemma thing, and it's a very important theorem. It characterizes UFD in terms of ideals, and we will see the power of this because we're going to use this to prove the following. So here is the last theorem of today, and we'll talk about why these are true tomorrow. Theorem 1128. Let R be a domain. We have 1 implies 2, implies 3, and none of these are reversible. in general. One, R is a Euclidean domain. Two, R is a principal ideal domain. Three, R is a UFD. So any Euclidean domain is a principal ideal domain. Any principal ideal domain is a UFD. And you can't reverse these in general. These are all. We'll tie this together next time. Any questions? Yes. I am. I had to make students this morning, but I promise you, I will get it over.
Hello. Like the one they put it to now?
Oh,
I'll send it.